Hi everyone, Marlen Roberts here. Advanced Analyses Made Easy. So I'm just going to go through some examples of what an advanced analysis is compared to a basic analysis. Then I'm going to give you a practical example using a Chisquare test and a logistic regression. And then we'll see just how easy we can make them by demonstrating them in our software, Intellectus Statistics. Why don't we get started? Let's start with section 1, comparing basic and advanced statistical methods. So as some of you may already know, some of you may not, most statistical problems have more than one right answer. You can use a variety of procedures to analyze any given problem. So it's not like there's this only one statistical analysis for my analysis or only one statistical analysis for my research question. You can actually use a variety of different statistical tests for determining what it is that you want to find out. So that being the case, generally you'll see this advanced versus basic terminology a lot. What makes an analysis advanced? What makes it basic? Really, these are subjective terms because when you get down to it, it's really just math. It's all the same thing. And I think that you'll find after you have a little bit more experience with these things that it's really not about the complexity of the analysis. It's about what question you're trying to ask and what's the most appropriate test to answer your question, or what can get at the underlying information you're trying to uncover in the most efficient or effective way. But for the purposes of this presentation, I'll go ahead and define some general properties that we'll use to help us differentiate between basic statistical methods and advanced statistical methods. So what I've chosen to define basic statistical methods are univariate or bivariate tests. Those are tests that may only include one or two variables rather than many. They usually won't have very many assumptions, maybe just a few or one or none, and they can usually be calculated by hand, so they don't require any sort of advanced software to actually perform these tests. Whereas advanced statistical methods include more than two variables, multivariate analyses. They'll have maybe multiple or complex assumptions that need to be tested before the validity of that analysis can be established. And they also are really complicated. It's difficult to calculate them by hand, if not impossible, and so it requires a computer to perform these calculations. So, given those two distinctions, let's move forward. So you might ask, well, if I can do the more basic analyses that don't require all these assumptions, why would I even want to use the advanced analysis? Isn't simpler better? And the answer to that is yes, it is. Simpler analyses are generally preferred if they answer the same question. I mean, there's something called Occam's razor, which says that given two solutions that produce the same result, you should choose the simpler one. And that's usually true, even in statistics. So that being the case, if you do have the option to use a basic analysis, you probably should. But there are sometimes different circumstances when you would want to use a more advanced analysis. They generally tend to include more complicated information, or more informative information, I should say. So whereas a basic analysis might just tell you whether or not an effect exists, an advanced analysis might tell you the strength and direction of that relationship. So you get a little bit more information there. Might help you to hone in on what it is you're trying to discover. And there are also some additional things to consider. I've listed out something called Simpson's paradox here and provided a small graph. What Simpson's paradox states is that when you don't include the proper controls, you might actually see a reversal of the relationship you're trying to identify. And you can see from this small scatter plot here that without controlling for those red and blue groups, which actually have positive relationships within each group, the dotted line represents the relationship when you do not include that grouping as part of your control. And so you can see it's actually a reversed relationship. It actually goes down as opposed to up. And so this is a situation where you do want to use a more advanced analysis, perhaps because otherwise you may have missed something very important about your data. Aren't advanced analyses more difficult, you might ask? Well, I would say that with today's computers and statistical programs, advanced analyses are just as easy as basic analyses. I mean, I don't know of anyone that really conducts statistics by hand for practical research anymore. It's just not done. And that being the case, advanced analyses are just as easy to conduct as basic analyses, assuming that you know what question you want to ask. And that's really the only hurdle around these advanced analyses, is knowing where can they be applied and when can they be applied, as opposed to a basic one. And as I said before, in many cases you can use more than one analysis to answer your question, and so you're not locked in. And so actually there may be more than one answer to that question. So to kind of illustrate my point, I've chosen to cover just, just a simple analysis, a chi-square that you may have seen in an introductory statistics course, and compare that with a binary logistic regression, which is generally thought of as a more advanced analysis. You may not see that until later in the course, if not in another course entirely. And so, there's a lot of methods I could cover, because advanced analyses is a very wide range of analyses. But for the purposes of this presentation, I think I'll just keep it simple and maybe show that some of these advanced analyses really aren't so scary, and that you can use them if you just know what to look for. What is a chi-square test? I'll just define it for those of you who may not know. So it's considered basic, and what it does is you're trying to establish whether or not two variables are related or not. So you're testing whether or not they could be considered independent is what you're doing. And usually your variables are categorical, so it would be like gender and political party affiliation, something along those lines. A chi-square test only uses two variables, so it matches one of our criteria for defining a basic analysis. The assumptions are very few. It only includes two of them, which is a sample size requirement and that the observations are independent, which is pretty much a universal assumption. Almost every single statistical analysis you'll ever see will have that independence of observations assumption. And lastly, you can conduct a chi-square by hand if you need to. It's not a very complicated analysis. So those three qualify it as a basic analysis. Whereas logistic regression is considered more advanced because it does use multiple variables, or few. It needs a minimum of two. And although there are not many assumptions, the calculations are extremely complex, and I don't think that you could really do them by hand unless you spent hours and hours writing things down, because it's an iterative procedure, meaning that there's not a single formula that just allows you to calculate the numbers. It really tries to hone in on the numbers by trying different values until you can find a solution that fits the data the best. So it usually requires a computer to do that. So that kind of outlines some of the differences between the two. Continuing on, what questions do they answer? Well, as I mentioned before, the chi-square tests whether two nominal, categorical, that is, variables are independent of one another. Whereas logistic regression, on the other hand, can still answer that question, but it takes a slightly different approach. And it tests whether the odds of an outcome can be predicted by one or more predictor variables. And what I mean by that, what I mean by outcome is you have some binary variables such as, let's say, purchase or not purchase, where a purchase would be a success and not purchasing would be a failure. And so you're trying to predict the success, so you're trying to predict when a customer is going to purchase something or when something is going to occur. So any type of situation when you have two possible values, you can assign one of them the outcome category and the other one the not outcome category, the reverse of that, and then you're trying to predict the outcome. So the way that you might apply that with a chi-square is you would just simply use both categories as one of your variables. Both of those categories would represent part of your table. So you can answer the same question. You can still get an idea of whether or not this binary variable is independent of some other variable, but the binary logistic regression is going to take a little bit more of a direct approach in telling you exactly how much of an effect is that some other variable has on that outcome. It allows you to control for any of those external effects, and it also allows you to work with more than just two variables, which can be an advantage sometimes. Just for a visual representation, I placed some of this information into a table about chi-square and logistic regression. So whereas chi-square is more exploratory because you only get that information about whether or not an effect exists or not, you don't really get strength of direction. You do get that in logistic regression, and hence it is a predictive analysis, in that you are trying to predict something, trying to expand whatever model you end up with to something that might happen in the future, because it's very useful to be able to know what future buyer behavior will be like as opposed to what you've already observed, because businesses or researchers in all kinds of different disciplines use logistic regression to try and say, well, what changes can we make to maximize our purchases next quarter or something like that. So you can use it in a predictive sort of setting. As far as the DVs and IVs are concerned, Chi-square doesn't use DVs or IVs. There's no designation placed on the variables, so that doesn't apply. Whereas in the logistic regression, you always have one dependent variable, which has two categories, and then you can have as many independent variables as you want, and they can be any level of measurement that you choose, either numeric or categorical. And then the basic question being asked, which is, under the chi-square case, are two variables independent of one another? And under the logistic regression case, can the odds of an outcome be predicted by a set of independent variables? Move on to the example. I just want to clarify that this is fake data. I made it up before this presentation, so don't think that any of the relationships shown here are real, but I think it's a real-world scenario that's possible, so I thought it was a good idea. So what I've got here is a political party affiliation, education, and gender. And I just generated 100 observations as though I were to have gone out and collected some survey of 100 people and had them respond with their political party affiliation, gender, and then their level of education, measured as either high school, undergraduate degree, or graduate degree. So the question I'm interested in knowing is political party independent of gender and education. So we could actually use either the chi-square or the logistic regression to solve this problem, to give me an answer. And I've phrased those questions for both cases here. So for the chi-square case, we're actually wondering, is political party independent of gender? Is political party independent of education? Whereas in the logistic regression case, we're still asking a similar question, but it's worded slightly different because you set it up a little bit differently. And as we said before, you're predicting an outcome. So in this case, we could just arbitrarily choose one of the parties to be our outcome. So in this case, there's two parties, party A and B. Let's just assign party B as our outcome, for example, and let's determine whether or not gender and education can successfully predict the outcome. So I want to know if gender and education can successfully predict someone choosing party B over party A. I think that for this analysis, personally, if I was doing this study, I would probably choose logistic regression. And here's a few reasons why. With the chi-square, all you're really going to determine is if there's evidence of a dependency between those two variables, which is good. I mean, we want to know that. But you could probably learn a little more by determining the extent of that dependency. As you can see here, they both answer that fundamental question of whether or not there's evidence of a dependency between those two variables, whereas the chi-square will only tell you whether or not your observed frequencies are higher or lower than you expected. Whereas in the logistic regression, you'll actually be able to estimate the strength and direction of that effect to say, well, okay, so let's say that gender is related to someone voting party B instead of party A. Well, how much more? How much more likely? Is it a lot? Is it a little? And you wouldn't be able to really know that very precisely with a chi-square test. And so this is one instance in which you might choose to use a more advanced analysis because it would be more informative. A side note, when you run a chi-square test, you're limited to only two variables, as I stated. So what that means is that in order to determine whether or not political party was independent of gender and education, you actually have to run two separate tests to determine that. Whereas with the logistic regression, you can include both of those variables in the same model, and you only have to run one test. And in statistics, when you run multiple tests, you actually increase your type 1 error rate. And what that is when you claim that there's significance when there's really not any in reality. That's a general rule for statistics, is the more tests that you conduct, the higher the likelihood that you're going to make a mistake and see something that looks significant, but it's really just based on randomness because you did so many tests. So doing fewer tests is better if you can do that. So in order to illustrate this, I thought that let's go ahead and run in our software, Intellectus Statistics. So I prepared a data set that has this information in it. Okay, so I've logged in, and I'm just on the home screen of our software here, Intellectus Statistics. So first what I'm going to do is click Upload, and then I'm going to pick the file that has the data that I want to analyze in it, example data. As we can see here, I've got my three variables, party, gender, and education. And if we just do a brief exploration, I can see the values here. So party A and B for party. Gender, we can see I have male and female. And then for education, I have high school, graduate degree, and undergraduate degree. So I won't recode any of those. I'll leave them all as nominal because that's what we want. So why don't we just proceed to manage our data. We can actually visually inspect this if we click on the bar plot option. And that actually is quite useful sometimes. because you can get a feel for what your data looks like before you even start analyzing it. And in this case, I'm just looking at a bar plot of party, where I can see that the frequency is a little bit higher for party A than B. We can also split that up by one of these other variables. So let's split it up by gender and see what we get. Okay, so it looks like for party A, there was definitely more males than females. And likewise in party B, there was definitely more females than males. We can see that from the frequencies. These frequencies are what the chi-square test looks at, by the way. So when we run the chi-square test, we'll actually see these frequencies in a table. And it'll tell us whether or not these differences are actually significant and worth noting, or whether or not they're just based on randomness and nothing important going on there. Let's look at education for good measure here. And for education, I'm definitely seeing a prevalence of the undergraduate degrees in comparison to the graduate degrees in party A, or in party B, excuse me. So that just gives a brief visual inspection. So why don't we go ahead and proceed to the analysis page and actually take a look at these. And we can see whether or not our advanced analysis has any better results than the chi-square test. The good thing about this software is that it's really not that difficult to run an analysis, so we can just compare both. Why don't we? Let's run the chi-square test first. So we'll choose party as our first variable and gender as our second variable. Then let's go ahead and add another one and take a look at the same party variable, but we'll also look at education. After we've added our analyses, all we have to do is conduct and download them. There we go. All right, so once you open up the document, you can see what we added here. So a chi-square test of independence between party and gender, and a chi-square test of independence between party and education. So after we scroll down, there will be some glossaries that explain what the terms and symbols will be in this document. We'll go down a little further, we'll see some raw output. This is usually what you get from some other statistical programs, where you have just some descriptive statistics first, followed by the results of each test. And as you can see here, it is populating that table with the same frequencies that we saw earlier. And there's a little bit of additional information, the results of the chi-square test here. You know, I can tell immediately that they were significant, but you know, for the untrained eye, that may not be as apparent. And so that's why we provide the written narrative, which is here. And this will just explain it to you in plain language. So we can actually see here that, okay, we conducted the chi-square test of independence. It tells you about the levels in each variable. It even handles the assumptions for us. I mentioned earlier there were two assumptions of the chi-square test, which is related to sample size and independence of observation. Well, you can only really test the sample size because independence is just an underlying assumption. But based on the sample size, which requires that 80% of the cells have expected values of at least 5, and that all cells have expected values greater than 0, we can see that 100% of the cells met those conditions. And so our assumptions are met, essentially. Then it goes down and breaks down the results for you. So it says that the results were significant, which is good. I mean, that's a great result for me, because that's what I wanted to know. I wanted to know whether or not political party and gender were related to one another, and based on the significance of this test, I can see that they are. And so as we go down, it says that the party B female and party A male. So within the party B and female category, there were definitely more observations than you would have expected. So, and we can see that in the table here. The expected values are inside these brackets, and we can see there was actually more females that voted for party B than you would have expected if they were all equally likely. For males in party A, we can see there were definitely more observations there than you would have expected, and far less in the inverse of those. So far less females than expected in party A, and then less males than expected in party B. So that kind of sums up the chi-square test for party and gender. And as you can see, I mean, you get an idea of probably what's going on, but it's hard to really know. It's hard to really quantify these values. It's hard to quantify these differences in terms of, well, how much of an effect was there? What was the effect size? You don't really have that for a chi-square test. And so in many ways, a logistic regression would be more effective in that regard. Of course, if all we were interested in was determining if there was a relationship, then we'd be done. And at this point, we would have established that. And so if this is all we're interested in, and it's the only question we want to know about, then the Chisquare test is perfectly fine. Let's take a look at the one for education, just to get an idea about that one as well. Once again, we ran through the assumptions, and 100% of the cells have the appropriate sample size, and so the assumption is met as well. And as we go through, we see that it was also significant. And as we go down and look at the table, we can see that, okay, there were fewer people with graduate degrees that voted for Party A, and more people with graduate degrees that voted for Party B. With high school, it looks like a similar trend. Actually, high school may not be that much different. 21 versus 17 and 12 versus 15. It's a little closer. Notice these values in the middle, they're expected frequencies, so they actually may not end up being whole numbers because it's based on averages. So 17.8, you know, what is 17.8 people? You can't do that, but it's just an average of what you would expect, and so it's close enough, I'd say. Whereas in the undergraduate degrees, you have a little bit less here, a little bit more there. But for the most part, I'd say that these differences are less extreme. But once again, with the Chisquare test, we can't quantify that. And we still showed a significant result. So there's definitely something going on here. Just for good measure, well, now that we've looked at those Chisquare tests, let's just clear them off, and let's run that binary logistic regression, and let's perform a comparison and see what the more advanced analysis tells us that maybe the Chisquare test did not. So it's as simple as choosing our party. We're going to leave Party A as the reference category. The reference category is just the opposite of the outcome. So if you want Party B to be the outcome, then it would be relative to A. So it's always the opposite. So it's success relative to failure. So we'll go ahead and leave that as Party A because we were interested in Party B. And then we'll just choose both of the variables that we're interested in and click Add Analysis. Once that's been conducted, we just click Conduct and Download again, and out comes our document. Okay. So we can see here we've added a binary logistic regression with party predicted by gender and education. As we go through the same story, we've got an explanation of what the binary logistic regression is used for, as well as a glossary of terms and symbols for those used within this analysis. And as we get down to the raw output, we see the same descriptive statistics as before, but a little bit of a different raw output here. We have the variance inflation factors, which is related to one of the assumptions of binary logistic regression. And then we have the regression table, which actually presents you with those measures of effects that I had mentioned earlier. So I won't spend a lot of time here. Let's just get straight to the write-up and see what this analysis is telling us. So it lists it out for us here. We conducted a binary logistic regression to examine whether gender and education had a significant effect on the odds of observing Party B. It's exactly what we asked in the presentation earlier. So, and it lets us just know for reference that the reference category was Party A. So binary logistic regression really doesn't have that many assumptions. One of the assumptions that does matter, though, is whether or not your independent variables are really related to one another. And this kind of causes problems when they are, because if you have two variables that are extremely related to another, then it could be argued that maybe you should just drop one of them. Let's take the most extreme example that I can think of, which would be, let's say you were trying to predict something like a person's weight from a person's height, but you had two height variables, one of them measured in inches and the other one measured in centimeters. Well, those are perfectly correlated. They're basically measuring the same thing. And so if you included both height in inches and height in centimeters in the model, the model is going to have trouble partitioning out which one is really explaining the variation in weight. Is it height in centimeters? Is it height in inches? And so at that point, you can't get much more inflated than that. So you might as well just drop one because they're perfectly correlated. So this can occur in other situations as well. Okay, continuing with what I was saying. So that can happen in the real world too with variables that are not perfectly correlated, but that may have a really, really high positive or negative relationship. So something that's really close to being the same but not quite the same can still have the same effects as that extreme example. So as we can see here, the various inflation factors were calculated, and it gives you a threshold value. In this case, VIS of 10 should be considered about the maximum upper limit, and we give a reference to that number. And then as we see the table here, they're both only 1, so it's almost not even an issue here. They're basically not related to one another, so we don't have to worry about that. In the next paragraph, we go into explaining the actual result. So we can see the overall model was significant, suggesting that gender and education had a significant effect on the odds of observing party B. Well, we already kind of knew that because we ran the chi-square tests and we saw that those were significant. And the binary logistic regression is going to provide a very similar result. So as we go down, we see our measures of effect size. In this case, we're using McFadden's R-squared. And it tells you that values of 0.2 are indicative of models with excellent fit. In this case, we had a McFadden's R-squared of 0.11, so we had a medium-ish effect. Not too large, but not small either. Right after the effect size, we get right into explaining those coefficients. And before I do that, why don't we just look at the table? This will list out everything in the table, but I think that seeing it visually can be a little bit more informative. So what this table is showing you, it actually partitions out these variables into categories. And by looking at these categories, we can actually get a measure of how much of an effect that category had. So generally, in a categorical variable, when you include it in an analysis like this, this also applies to things like multiple linear regression or analysis of variance. You end up dropping one of the categories because it's all relative to that category. So in this case, there's two categories in gender, male and female. So when we look at the coefficient for gender male, we're saying that this is the amount that's different from the category of female. The same with these two. This is the amount that's different from the one that's missing, in this case, graduate degree. So it's high school relative to graduate degree. It's undergraduate degree relative to graduate degree. And as we look at these values, we can see these odds ratios over here. That's what OR stands for. And what an odds ratio is, it tells you the ratio of how likely the outcome would be. In this case, our outcome was political party affiliation with party B. And it tells you how likely that outcome is given that membership within these groups. And so now that you've seen the table, let's actually go look at these sentences and see what they say about that. So let's go to the first one here. So in this instance, being male was significant, and your odds ratio for that was 0.32. And what that means is that for males, the odds of being in the party B category, so in other words, the odds of voting for party B would decrease by 68%. And that's a pretty strong statement considering when we looked at let's see, I think I still have my other document up as well. When we looked at that, we can see that, let me try and scroll in here. So let's just compare those and see if it's the same. So get back down to where I was. Okay, so what did we just say? We said that, okay, for males, they were 68% less likely to vote for party B. So why don't we look at the other document and take a look at that as well. And so males, party B, and we actually do see that there were less observed than you would have expected if these were equally likely. So it actually confirms that result. So what we're seeing here is the chi-square test confirming what we're seeing in the logistic regression. As we look through some of the others, we'll see very similar patterns. We can see that for education high school, we can see that the odds ratio was a 0.28. So that means that it's 1 minus that number if you're wondering where these percentages are coming from. So 1 minus 0.28 is 0.72 or 72%. And since the number is less than 1, that means that it is decreasing. So that's the way odds ratios work. If you take a ratio, if the number on top is larger, it'll be greater than 1. If you take a number on top that's smaller than the number on the bottom, then it'll be less than 1. So it's just, and so that's literally what an odds ratio is. We're calculating the probability of an event occurring, compared to the probability of an event not occurring. And so if you have values greater than 1, that means it's more likely to occur, whereas values less than 1 means that it's less likely to occur. It's really not as, I know that may sound a little bit complicated for those of you that may not have a lot of experience with logistic models, but really when you think about it, that's sort of exactly what the chi-square test is doing as well. You're just determining whether or not the probability of observing this value is less than or higher than observing this value. And if it's smaller than the expected value, you know that that number is less. And if it's larger, you know that it's more. So really, you're just looking at the same information, only the logistic regression presents it in a more accurate way. And you can actually gauge these numbers in terms of how large or small they are. I mean, you might end up with a significant result, but only have a 1% decrease, which may not be that meaningful, even if the model actually showed significance. So that logistic regression in many ways can be more informative. This is from Mark. He asks, what about a complex multi-possible result that has the type of multiple alternative decisions to accomplish an acceptable solution? So Mark, okay, if I understand what you're asking correctly, you're saying that what happens when you have more than one outcome, like more than just two? That's actually possible, and logistic models actually can extend to the situation where you have more than just one outcome. And actually, it would look something similar to this. In fact, you know, why don't I just do this? We actually do have a model that has, or a variable that has 3 outcomes. So this is a little different. I'm not sure what these results will look like, but let's just run it. So in the case when you do have more than one outcome, there's an extension of the binary logistic regression model called multinomial logistic regression. This allows you to take a dependent variable that has more than just 2 levels. So let's go ahead and select education as our dependent variable, and we'll just choose the reference category as high school, and then we'll choose party and gender to predict that. I mean, like I said, I don't know what this model will look like, but we can just take a look and see. Okay, so having conducted this, what we see is a multinomial logistic regression with education predicted by party and gender. I mean, this doesn't make a whole lot of sense predicting education, because education is usually something that will be independent of some choice that somebody would make, like party affiliation. But we can still at least look at the calculations and get an idea of what it would look like when you do have a multi-outcome dependent variable. So we'll go through the glossary. By the way, for those of you that may have wanted to see this, we can see the definitions of what those coefficients mean in this case. So in that case, the beta is the slope of the predictor with the log odds of the dependent variable. And like I said, the log odds is just, it's basically a ratio of the probability of an outcome compared to the probability of the opposite. So in this case, the outcome is, we're referencing everything to high school. So it would be undergraduate relative to high school, and then it would be graduate relative to high school. And we'll actually see that in the result. We'll see 2 tables because we're comparing both of them to our reference of high school. And then our standard error is just, you know, how reliable is our beta. And then the odds ratio, it's the same thing as the beta, it's just the exponentiated version. So you take the, you know, e to the beta essentially is what the odds ratio is. And we list that out right here, exp beta. So it's just a direct transformation. And the reason for that is because in the logistic regression, the dependent variable is transformed using the logarithm. And I mean, I'm taking everybody back to their algebra classes right now, but the way that you cancel out a logarithm is by taking the exponential. So, you know, if this is a logarithm here, oh, I don't have editing on, but yeah, if this is a logarithm here, then by taking the exponential, you essentially cancel those out, and what you end up with is the actual value of beta, only unexponentiated. So well, let's get down and let's see what we actually got with this. So what we can see here are our tables in the raw output, and you can see that there's 2 tables rather than just 1, and they actually look very similar to what we saw in the binary logistic. In fact, they are the same. It just extends it into the case when you have more than one outcome. And so to answer Mark's question about having multiple outcomes, that's actually exactly what this extension does, is it compares both of the alternatives to the reference category, in this case, high school. So we have the response graduate degree and the response undergraduate degree, both compared to high school. As we go through, we can see that those VIFs, which that stands for variance inflation factors, by the way, and all that is you can basically think of it as a measure of correlation, because that's essentially what you're doing. You're just determining the level in which, the level at which your independent variables are related to one another. And the reason it's called an inflation factor is because it tends to inflate the error variance. So this number up here that we saw, the standard error, it tends to inflate that number the more correlated your variables are. So you want those to be relatively uncorrelated. As we go down into the table, we see it was not significant, which is not really surprising. Running the model backwards like this, I wasn't expecting much. And actually, this is good because I can actually show what an odds ratio that's not significant looks like. So
let's just go from the top here. So the results were not significant, suggesting that party and gender did not have a significant effect on the odds of observing any response category of education relative to high school. So that means it wasn't significant for anything. As we can look at that, the same value as before, the McFadden's R-squared. It's just a measure of effect size that tells you about, approximately how much you can expect to rely on your results. So if it's a large value, then that means that the difference was, it's like a ratio. It was a really high, it explained a lot more of the variation in comparison to the model without any of these predictors. So like adding party and gender would have, in this case, only explained about, maybe 3% more. It's not really accurate to interpret this as a percentage, so I won't say to quote me on that, but basically with values that are larger, then that means there was a much larger effect. And in this case, it's not very large at all. So there wasn't much of one. As we go through the results, we can actually see that there wasn't much of anything really. I mean, what we see right here is an odds ratio of 1, essentially is what that's saying. And what that means is that it was equally likely. Being male versus being female didn't have any effect on having a graduate degree versus having a high school diploma. So really, I guess what you can infer from that is that males and females were about equally distributed between the different education categories. So it wasn't like one gender had higher education than the other gender. This one's a little bit interesting. This one makes it seem like these are related because obviously we looked at these in the opposite direction and they were significant. What this is showing is that people with a graduate degree were about 3 times more likely to be in Party B than people with high school diplomas. I mean, I think it's starting to get confusing now because we're looking at this from sort of a question that you wouldn't normally ask in the real world, but you can kind of see parallels between the analysis we were in earlier and the one we're at now. Okay, let's see here. So Colleen asks, if you have multiple measures for one hypothesis, how do you decide which measures to keep? So I see. So you're saying that, okay, and there's an additional part here. So should the hypothesis 1 overall be more significant than the individuals? I see. Okay, so well, I think what you're asking here is if you do have multiple predictors, like in this case we have party and gender both predicting our outcome, and do we decide whether or not we need to keep those or not? Well, there are ways where you can, you might run a model and determine that. In this case, we actually saw that gender male was not significant, and whereas party was significant based on the p-value here. Although there's controls for this because the overall model was not significant, which is probably the most important thing in this instance. Even though we do see that one of the predictors, using, of course, 0.05 as the significance level, which is really common in most social science statistical type settings, it was less than that value. So we actually do see something significant in this model, but it really wasn't significant overall. And to answer your question, Colleen, I wouldn't necessarily recommend removing anything that's not significant, just because that doesn't really make sense on a theoretical perspective. Like generally what happens in any type of research is you decide beforehand what relationships you believe are important, and then you test for those relationships, and you don't really do a whole lot of adjusting after that. I mean, you might, if you have a lot of controls and one of the controls seems to be messing up your model because it's just so badly related, then maybe you could drop it if it's not really related to your hypothesis. But if you have a variable that's related to your hypothesis, I would almost never recommend dropping it, just because this is important information. Even though we could probably drop gender and we might actually see a flip in the model significance, I think that we probably would want to keep it in this case, because what that's doing is it's showing us that really, despite having this one significant effect, I mean, when you look at everything together, there's really not a whole lot going on. And just for the record, I made this data set up, so I happen to know that there is absolutely no relationship between education and gender in any way. So this model is actually accurate. And in fact, it was so insignificant that it even bled over into removing that significance from party as well. And so just depending on the question you're asking, it really determines whether or not you need to keep what you can. But that being said, I would say a good way to do it is to go ahead and run the analysis, look at these p-values, look at those effect sizes, determine which ones look like they truly are having an effect, and which ones are not. And if they truly aren't, then you could probably exclude the ones relatively safely in most cases. Melanie asks, I'm proposing a sample of adult children that covers World War II through the Gulf War. I would definitely need a regression analysis, correct? Well, Melanie, I guess that depends on what it is exactly that you want to find out. So what types of variables are you using? You know, what's your main outcome that you're looking for? Without that information, it's hard for me to really say. We have a question from Irene about dummy coding. Okay, Irene, that's a good question because I think that kind of got slipped in here and I didn't explain it very well. So Irene's right. What dummy coding is what we're seeing right here, where you see this, you know, the variable name was party and then the category name was party B. You know, and why does it look like that? Why do we see party B when really our variable is named party? Well, that happens because of a process called dummy coding. And what that is, what a dummy variable is, it's basically an indicator variable for a particular category of a multi-categorical variable. So if you have a variable that has 2 or 3 categories, rather you can't do calculations on categories. They're just characters. You know, they're letters and not numbers. And so dummy coding is a way of expanding that out into a series of, well, they're called dummy variables. There's really no other word for them. And essentially what they are is a sequence of zeros and ones. To explain this, I'll just do one in an Excel document for everyone here. So let's just say I have a variable called, well, let's use education. That's a good one. So education may have 3 categories, and I'll just use simple letters for now to make it easy. So we'll do A, B, C, A, B, C, A, B, C. Okay, so we've got a few categories here. If we wanted to include that in our analysis, you know, we're going to have to dummy code this because these are letters. So dummy coding is actually relatively simple. I'll just explain it over here 2 columns to the right. So what you would have is you have 3 categories, so you're going to end up with 3 columns. We have the column for A, the column for B, and the column for C. And then it's simply going down and saying, well, where does A occur? Okay, there's an A, there's an A, there's an A, and then everything else is a 0 because we've covered all the A's. And then the same thing for B. You know, we have a B here, we've got a B here, and a B here. And then we have zeros everywhere else. And then the same thing for C. We have a C here, and a C here, and a C here. And then everything else is a 0. Okay. And like I said before, you end up dropping one of these because you actually have the intercept. And what the intercept is, and I'm not even sure if we include that. Let me look at this document. Okay, we actually do include that. I don't talk about the intercept because usually you don't even interpret the intercept. It's not too important. All the intercept does is provide a baseline. So in this case, it would be almost 50%. I mean, equally likely either way because that's the baseline for what you're starting with, and you're really just determining whether or not these individual categories and the baseline add something or subtract something from the overall. So in the intercept, I mean, this is not too important for what we're talking about, but the intercept would just be all ones. And that's not important. The ones don't mean anything. All that means is that in the calculations, it gives you a constant to start from. And that being the case, since you already have all these ones, you actually can just drop one of these categories because it becomes redundant. You don't need it. So this would be the actual data frame that is used to calculate the model. And that's why when we actually look at this model, we see party B, because party A was omitted. We don't need it. And we see gender male because female was omitted. We don't need that one. So that's why that looks like that. And the same thing for the binary model that we had before, where we only have high school and undergraduate because we omitted graduate because we don't need that one. We have that information is already absorbed into the intercept term. And that has a little bit of an implication because what it means is that when you look at this, this means that people that were in high school were, let's see, less likely, you know, 28 would be the 72%. They were 72% less likely than people with graduate degrees. See how that works? When it gets intercepted, when it gets absorbed into the intercept, it becomes sort of a reference for you. So it's high school in reference to graduate degrees, undergraduate degrees relative to graduate degrees. And so dummy coding is a very effective way of taking information that has letters and making it numeric so that you can use it in an analysis. I hope that I explained that well enough. Oh, I see. Okay, well, we got a little more from Melanie, talking a little bit more about her study. So in this instance, she wants to know whether or not the father had post-traumatic stress disorder and was a combat veteran. Well, you could analyze those. Well, I mean, the way it sounds to me, it looks like
looks like what you want to know is whether or not someone being a combat veteran is more likely to cause them to have PTSD later in life, which is a valid question. And yes, to answer your question, you could use a logistic regression for that, but there's also no reason why you wouldn't be able to use a chi-square for that. I mean, that's the thing about statistics, is that a lot of times you can use multiple analyses to answer your question, and that's generally, I think I've been saying that a lot. But the real question is there anything else that might affect post-traumatic stress disorder? Could there be other risk factors other than just being a combat veteran that may have an effect on that? And if you believe that that's the case, then it would probably be a better option to go with logistic regression, because you could control for those other effects too. Whereas a chi-square test may be a little bit misleading. You might find that, oh, it's really significant. That must mean that being a combat veteran causes post-traumatic stress disorder. But what if there was a history of psychological illness in their family or something? That might also have a strong effect. And so it's hard to know with the chi-square if that type of thing is occurring. Somebody asked about our software and the cost of it. So right now, actually, we're offering free trials. So you can always create a free account. I don't think we offer all of the analyses listed, but if you're interested in trying it out, you can just go straight over to analyze.intellectusstatistics.com and just sign up for a free account, and then try the analyses that we do offer for free. And I think you can sign up for a subscription for $59.99 for a month. So a 30-day subscription is $59, but you can always try it out for free first. So yeah, I mean, our software, I really think it's great. It's definitely a work in progress. We're continuing to develop it all the time. So the analysis list that you see here it will continue to grow eventually. And some of these are not available yet. I would have to mention I'm on my administrative menu, so some of these are in-progress works that are not available yet. But we do offer everything up through the Kruskal-Wallis test, and we're working on adding some of these more advanced analyses. There goes that subjective term advanced again. I guess it's what we consider advanced, which would be some of these. But we definitely offer up through non-parametric analyses. We offer more predictive analyses as well. And the goal of our software is to try and make most of these analyses as simple as possible by avoiding the user having to know anything about programming or even really about some of the more advanced concepts of statistics. As you saw earlier, it includes the assumption tests for you automatically. It includes a written template that you can use as a starting point automatically. It includes the raw output as well as glossaries, and it just tries to help you out as much as it can. And most of the user interface is just point and click. Descriptive statistics, for example, as simple as clicking your variables and saying add analysis, and that's it. I mean, conduct a download, and there we have it. We have descriptives right away. And as we go through, we can see every document pretty much has one of these glossaries. In this case, we only have frequencies, percentages, a couple statistics that you may or may not have heard of. We get down through that raw output, and then we get to those results. And it pretty much includes all the relevant information. And it's not, it may not be perfect every time because of the fact that it is a computer program, and it has to be repetitive in some ways. In this case, we just choose the maximum category because we feel that would probably be the most interesting thing about descriptive statistics. But it also provides you with base language that you can use as a guide to help you write a dissertation or help format the tables for you in your research paper. And there's a lot of different uses for this. And I think that it could be really useful for a lot of people. I haven't ever heard of a committee pushing back against a tool like this because it's software and it's available to everyone. I mean, I don't think that it would ever be recommended. I definitely wouldn't recommend downloading a document and turning it in directly. I mean, this is primarily a tool to use. It's primarily a way for you to get a template to help you understand the information, help you get a template that you can help format your tables, because a lot of times making these tables takes up hours. I mean, it takes a lot of time to get this information formatted into a reasonable and descriptive visualization. And so being able to get this stuff done for you automatically is really great. And I don't know of a committee anywhere that would be, opposing to you using a tool to help you format your tables or help you get your sentence structure in line. I mean,
quite frankly, this is no different than SPSS or SAS or any other statistical program. We still provide raw output. We still provide the same exact output that those other programs would offer, only we just restructure it and provide a little bit of written narrative around that helps you get a better starting point. Whereas with those other software programs, you may have to do that all by yourself. If you do cite the software, we actually provide a citation for you. Somebody asked about a citation down here, and we just include the citation for you here. So feel free to include that. How does the software take care of data modifications that have to be made, such as the log transformation prior to conducting analysis? That's a good question. Actually, so our software, we don't save any data in our software. The moment that you upload it, it's a temporary session until you're done. And so some changes can be saved, some changes can't, but most of them can be. In this case, let's say that I wanted to convert party for whatever reason to a scale variable. Usually we're doing this the opposite way. You usually have numbers that you want to convert to categories, but we can also go the opposite direction. So let's say that we just convert party A to 0 and party B to a 1, and then say accept changes. At that point, from this variable has now been changed. And from the next page, we can just download the data set. And yes, it does come out of the CSV file, by the way, or an Excel file. I mean, you can open CSVs in Excel, no problem. And what we can see now is that our variable called party has now been recoded with those zeros and ones that we chose. And that's only for recoding variables. Actually, for transformations, as we can see here, we do have a transformation tool. And I only have the one numeric variable because I just created it. But if we were to apply some type of transformation, let's say a square root transformation, for example, we can add that transformation. But this won't actually do anything to our original variable of party. This actually adds a variable, party square root. And if we download the data again, we can see that has been appended onto the data set. So to answer your question, data modifications are usually done on the file itself. And you can always download that file and upload it the next time if you'd like to use this. Because I can actually save this, and if I want to preserve some of these extra variables or some of the changes I made, I can just upload that next time whenever I go back to the upload screen, and then I'll have those same changes. Like I said, that really only works for some things. There's just a few things that may not be saved. For example, if I have this variable as scale and I decide to assign it an ordinal value, this is something you might have to do each time. Unless, of course, well, and even with categories, simply because the way the software works is by reading in numbers and characters rather than having any sort of meta information. And that keeps it light. It is a web application, so it keeps you from having to do too much, have to have your data formatted in a special way or anything. I mean, pretty much any Excel file or CSV file will work. So even though I will say that we are adding functionality in the near future for SPSS file types. And so, of course, those file types are more complex, and they will include things like value labels and ordinal or nominal levels of measurement, which would be preserved. So, but that we don't offer that right now, but we will. Somebody asked whether or not the data upload feature was related to the subscription service, and the answer is no, it's not. It's independent. So that uploading feature is just present regardless of your subscription status. But as I say, this is a developing product, and we are happy to listen to user feedback. And I think that at any point in the future, we may have maybe our own data format that saves this information for you. So, I mean, what you're seeing now, although I think it's already extremely useful, is still going to continue to grow and become ever more useful in the future. You know what? I think that's just about all the time I have today for questions, but if you have any other questions, you can definitely email them to, what's the address? Oh, and the email address you can send it to will be placed in the chat. You can send any additional questions to that email, and we'd be happy to get back to you. So I'd like to thank you all for attending. I mean, I enjoyed this webinar. I hope I explained things well enough, and if I didn't, be sure to let me know, and I'll do better next time. So thank you all, and I hope you have a good rest of your evening.